In this lecture we carry on learning a few useful things about graphs that follow on from our previous lecture. So just to remind you, we know that the graph consists of a set of vertices and a set of edges, which link the various vertices. And we've seen different kinds of graphs, so the ones in this diagram are what are called undirected graphs, but we've seen graphs that have direction on each of the vertices. We've also seen things called multigraphs, which can have multiple edges linking the same two vertices and may be directed or undirected. So now we talk about a way of getting more graphs out of a single graph, and one of these ideas is a subgraph. So if we have a graph of any kind, then we can create a subgraph if we take some vertices from the original graph and some edges. But we have to be a little careful how we do this. So we have that a graph is a subgraph of some other graph if the vertex set of our new graph is entirely contained in the vertex set of the original graph, and any edges in our new graph were originally edges in the bigger, larger graph, and the vertices of those edges are in the vertex set of the subgraph. So the general idea is that if you have some graph, for example, here's just a quick sketch of an undirected graph, we can create a subgraph by removing some vertices. So let's remove that vertex, and then we remove all the edges that include the removed vertices. So that means we have to remove that edge, and that edge. And then if we want to do any more than that, we could remove another edge. So for example, we could remove that edge, in which case we're just left with this graph here. And notice, if we check this, our vertex set of the new graph was included in the vertex set of the old graph. I haven't put in any new vertices. And our edges are only our edges that were originally in the old graph and are included in the vertex and have vertices that are included in the vertices of the new graph. The reason that we have this somewhat wordy definition is that we want to make sure when we're talking about a subgraph that we don't end up with a graph that has some edge that doesn't include a vertex at both ends. So that's, if you read carefully, you'll see that's kind of, we're plugging holes with that definition to make sure this doesn't happen. So once we have a subgraph, there are two particular types of subgraph that we're interested in. So if we only remove edges that include removed vertices, then we say that G is an induced subgraph. So the idea is you remove some vertices, and then any edges that are affected by having those vertices removed are the ones that you remove as well. So that's called an induced subgraph. On the other hand, we have that a graph is a spanning subgraph if the vertex sets of the two are the same. So we haven't removed any vertices, but we might have removed a few edges. So let's have a look at some examples. So let's just make a note. So this is our original graph. This is our original graph. Let's call it G. And let's have a look and see. So I'm contemplating this subgraph. Let's just check that it's a subgraph. Well, what's happened? We've removed the vertex labeled number 5, and we removed the edges associated with it. But we also removed the edge linking 4 and 1. So from this we can see that this is not an induced subgraph or a spanning subgraph, because we took away this edge here, so that means it can't be an induced subgraph, and we took away a vertex, so it can't be a spanning subgraph. Now if we have a look at the graph on the bottom left, so we're having a look at this graph over here, we haven't taken away any vertices. You can just check 1, 2, 3, 4, 5, 6, they're all still there. All we've done is remove a couple of edges. So we removed this edge between 4 and 6, and we removed these two edges as well. So since we didn't remove any vertices, this is a spanning subgraph. And then finally, if we look at our last graph, we haven't removed any vertices, so it is spanning. And if we have a think, we want to think about it, is it induced? Well, we've removed some edges that didn't belong to vertices, so it's not induced. And if we think back to our first spanning subgraph, that's also not induced. So one of the things that it's important to be able to do with graphs is to see whether two graphs are actually representing the same data. What do I mean? If we have a look at these two graphs in blue here, I could label the vertices of the B graph as follows. And if I consider the graph A, it looks quite different. But notice that if I label my indices very carefully, so I start at A and then I'm going to follow along to the next vertex B, and then I'm going to label this top vertex C, follow that down to D, across to E, and then I'm back. If I was to kind of unwrap the star shape, I would in fact end up with the pentagon that we've got on the right. So if we have graphs which can morph from one to the other without breaking any edges or removing any vertices, we call them isomorphic. So let's take a moment to have a look at this example over here. So take a moment and see if you can find labeling for the second graph that makes it isomorphic to the first graph on the left here. So one way to think about this is if we look at the graph on the left, the vertex A has to be, it has 4 edges emerging from it. So if we want to think about which one we could label A in our second graph, it's either going to be vertex 1 or vertex 2. Now notice that A has an edge that leads into it, followed by an edge that leads into it, followed by 2 edges that lead out of it. And if we have a look at vertex 1, we've got an edge that leads into it, an edge that leads into it, and 2 edges that lead out. On the other hand, if we look at vertex 2, this has 3 edges going into it and 1 going out, so it can't take the role of A. So it must be that vertex 1 is taking the role of A. So now if we follow through as we did in the previous example, we can see that the edge that goes from A to B by itself must be this edge here, so we'll label 3 as B, and we must have that D as 2, and finally that C is 4. So this is a relabeling that if this graph was made of string with connected to little ping pong balls or something, you could reshape it so that you ended up with this graph. And similarly, if you took the graph on the left, you could reshape it and end up with the graph on the right. So these two graphs are also isomorphic. It's worth knowing what this word means. So morphic refers to shape. And you know that iso refers to same. So the word isomorphic is meaning same shape, or can be morphed into the same shape. If we want to be fancy and have a mathematical way of saying that two graphs are isomorphic, then here's the definition that we need. So we're working with two graphs, and they're isomorphic if there exists a bijection. So remember, a bijection is 1 to 1 and onto. So our two graphs are isomorphic if we can find a 1 to 1 and onto function mapping one to the other, such that if we have an edge in the first set, then when we take the function that maps vertices to vertices, we end up with an edge in the second set. For multigraphs, we can add that the number of edges must be equal to the number of edges in the mapped graph. So now we're going to have a look at several different ways of storing information about graph structures that make it easier to do computations with them. So one of the most common types of data structure used for storing graphs is called the adjacency matrix. And the idea here is that we use a matrix, so it's going to be an n by n, because we're assuming that we have n vertices on our graph that are labeled 1 through n. And the entry ij, we will put a 1 if and only if the vertex I is connected to the vertex j. So we get 1 if vertex I linked by an edge to vertex j. So as an example, we have this graph here. I'm going to make it a little directed graph. And I'm going to label A, B, C, D. And we choose how we label them from 1 to 3, from 1 to 4. I'm going to call this just 1, 2, 3, 4. Then I know that I've got 4 nodes, or vertices, so I'm going to have a 4 by 4 matrix. So the row numbers represent the starting vertices, and the column numbers represent the terminating or ending vertices. So if we have a look, our diagonal will be any vertices that are linked to themselves. So on our diagonal we'll have any loops, but if we have a look at this graph over here, we don't have any loops, so we're going to have zeros on the diagonal. But now let's try and put in the data about each about each edge. Well, we have an edge that goes from B, which is 2, to A. So our starting vertex here is going to be the second vertex, and it's going to go to the first vertex. So we put a 1 in this position here, so this says started vertex 2 and draw an edge towards vertex 1. If we have a look at this second edge that we have here, that goes from 1 to 3. So from 1 to 3, I'll put a 1 in over there. Now we've got a case where we've got two edges that start at 3 and end at 4. So when we start at 3 and end at 4, we're actually going to put a 2 in over here. It's kind of like we put in 1 for the first edge and then we add in another 1 for the second edge. And that encapsulates all the information about edges. So we don't have any edge going from 3 to 1 or from 4 to 1 or any of the other options. So these points just get filled in with 0. So that nicely encapsulates all the information about this directed graph. We can also have a look at the adjacency matrix of an undirected graph. So let's just take a simple example like so. I'm going to label the vertices 1, 2, 3, and 4. And now if we put together the adjacency matrix, again it's going to be a 4 by 4 matrix. Just making sure that I'm going to get all my entries. So one of the first things we can see is we don't have any loops, so we're going to again have zeros all down the diagonal. But now, if we think about the edge that links 1 and 2, we can think of it as an edge from 1 to 2, but equally as well from 2 to 1. So in fact, we're going to put two entries representing this edge. We're going to put an entry from 1 to 2, and we're also going to put an entry from 2 to 1. So that tells us that if we know that we're dealing with an undirected graph, this just confirms that we have an edge from 1 to 2, which is also the same as an edge from 2 to 1. So there is some duplication of information when you're dealing with undirected graphs and their adjacency matrices. If we want to fill in the rest of the adjacency matrix, well, let's look at this edge going from 1 to 3. So this is an edge going from 1 to 3, so we put a 1 there, but it's also, we can think of it as an edge going from 3 to 1, so we have a 1 over there. And then finally, we can have the edge going from 4 to 3 and 3 to 4, so that's 3 to 4 is going to give us a 1 there, but also we can think of it as going from 4 to 3, so we have a 1 over there. We don't have any other edges, so we just fill in all the rest with zeros. So the thing that you'll notice about an undirected graph is if we look around the diagonal, then this matrix is actually symmetric about the diagonal. So you've got 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0. So that's a feature of adjacency matrices of undirected graphs. So the adjacency matrix is very useful, but there are a couple of other data structures that we can also use. So we have the idea of an edge dictionary. So what we do is for each vertex in our graph, we keep a list of edges that initiate at that vertex. The way that we do this is we're going to say that G represents the graph's edge information, and we note Gi is the list of vertices that are ending vertices for edges that start at vertex I. So the idea would be that you have your various vertices. So let's take our directed graph as an example. So here we've got our vertices 1, 2, 3, 4. And I'm thinking of 1 as the starting place for edges. So the only edge that we have here goes to 3. So we'd have 3. If we look at 2, the only edge that initiates from 2 is the one that goes to 1. And from 3 we have an edge from 3 to 4, and we don't have anything initiating from 4. So this is not particularly useful notation. This is often used in computation, and so we have various different syntaxes that we'll see for that. The third data structure that we can use is called an edge list. So a simple way of representing the edges is simply just to keep a list of ordered pairs if we're talking about a directed graph, or two-element sets when we're talking about an undirected graph. We are not really going to use this much at all, but it's good for you to know about it if you come across it when you're working with graphs somewhere else. So let's just work through an example using this directed graph. So let's see what the adjacency matrix should look like. So first of all, we notice that we have an edge from 3 to itself, so that's going to be a loop. And if we're imagining that each of our rows represents the initial vertex and each of our columns represents the terminal vertex, then we will have an edge from 3 to 3, which gives us a 1 on the diagonal. And now if we have a look at the edge from 2 to 3, then we need to have an edge that goes from 2 to 3, and we have indeed got a 1 in that position over there. Now we have a look at edges from 1 to 2, and we've got from 1 to 2, so we've got a 1 in that position there. And we have something from 2 to 4, so we go from row 2 to row 4, and we have a 1 in that position. And then finally, if we have a look at what's going on between 1 and 4, we have something from 1 to 4, but we also have something from 4 to 1. So we've got something from 1 to 4, which is that one over there, and diagonally opposite we've got from 4 to 1. And everything else is zeros. So notice that with this information, if we know that our graph has exactly 4 vertices, we can draw the directed graph fine. What would the edge dictionary for this graph look like? Well, we list each of the vertices, and then we create a list of all the other vertices that are linked to that vertex. So for example, if we look at vertex 1, then it is the start point. So we're thinking of that as the start. It is the start point for an edge to 2 and an edge to 4. If we have a look at vertex 2, which is this one over here, it is the start of a vertex that goes of an edge that goes to 3, and also an edge that goes to 4. Little old 3, the only edge that starts from 3 actually ends in 3 as well. So we have 3 as a terminal vertex for that. And then finally, if we have a look at 4, the only edge that starts at 4 is the one that heads to 1, and so we've got 1 as the terminal vertex for that edge. And finally, you could also just have a list of edges, and you can check for yourself that this is correctly telling us we have an edge starting from 1 and going to 2. So that's that edge. We have one going from 1 to 4, and so on and so on. Notice that we should have 2 entries involving 1 and 4, we have 1 and 4, so that says the starting at 1 and going to 4, and we also have 4 to 1, which gives us the edge that goes from 4 to 1. So we'll just make a little note. This is split there. So each of these different representations has different strengths and uses. The work that I've done usually involves the adjacency matrix, but I know that the edge dictionary also can get used quite often.